Hello, I'm Sophia here with my group mates Brandon, Zach, and Jackie, and we'll be discussing our project, the Sushi Maker.
Learning the art of making sashimi typically takes years, and most industrial sushi makers cost thousands of dollars and take up a lot of space. So, what is a person or small business to do? Designed to be affordable, space efficient, and with potential to fit into a system that would create whole sashimi, our Sushi Maker is the first step towards efficiently making sashimi at a fraction of the typical cost. Using our rice shaper is incredibly easy. Simply turn the wheel to make sure the mechanism is open, fill the space with rice, push the lever in the front down, rotate the wheel with your thumb and forefinger, then rotate the wheel the opposite direction, push the lever up, and voila, perfectly shaped rice every time.
Our Sushi Maker has three main mechanisms, the rice shaper, the elevator, and the fish drawer. To make sushi, first the rice shaper mechanism and the elevator work together to shape the rice. Next, the elevator is backed up and the fish drawer is open to set the fish onto the shaped rice. Lastly, the fish drawers would be closed and the elevator would be lowered to press the fish into the rice. The fish drawer mechanism is a modified four-bar to control both doors simultaneously. The elevator is a classic crank slider. The rice shaper mechanism is the most complex with four crank sliders driven by one control wheel. Our kinematic synthesis focuses on the rice shaper mechanism to ensure it met the acceleration and displacement requirements necessary to shape the rice.
The linkages we are analyzing are all four-bar crank sliders. Figure 2 shows the ground link in green/gray. Figure 1 shows the gear-shaped input link, yellow coupler links, and red output links. The gold input link shown is not a part of the mechanism. It is for analysis purposes only. Theta 2 is measured from the negative x-axis to the gold link. Looking at the top graph shows link 4 moving horizontally inward as theta 2 increases, and looking at the lower graph, we can see that the link is accelerating towards the center of the mechanism. Looking at the graphs on the right, they look very similar to the graphs on the last slide. However, rather than being in the horizontal plane, they are in the vertical plane.
Our force analysis was designed around finding how much force the user needs to exert on the driver wheel to get the requisite force necessary to shape the rice. Through research and experimentation, the force necessary to shape the rice was determined to be roughly 0.98 newtons. To reduce the complexity of the analysis, we analyzed the more concerning pair of rice pushers pictured below as link 3A and 3B. The main forces present in the system become the rice compression force, the user application force, and the force felt in the pin linking link 2 to link 3A and B. We then found the three equations of motion for each link by summing the forces in the x direction, the y direction, and the moments. After removing the redundant equations, we made the matrix pictured on screen. Using the inverse matrix method gave us the force values seen on the right. Since the user application's force, Ft, is so small, we can confirm that our design goal of making the product usable for anyone will be met.
Our most concerning failure mode is tear out because our thinnest parts are the coupler links and they are experiencing tensile stress. Tear out is the double shear of the red area shown on the left. Evaluating aluminum coupler links revealed a safety factor of 6,275.
The prototype is made of PLA and stainless steel round bar. Most of the parts were printed by an Ender 3 3D printer. Most design changes implemented during prototyping were functionality improvements or for ease of assembly.
Thank you for listening to our presentation.